Hey folks, this is lesson 6 in dynamics, and in this lesson we're going to talk about reference frames and go deep into reference frames, apply that to vectors, and then finally start converting between some coordinate systems. So we have previously defined reference frames in a very qualitative sense, and that was simply the point of view in which you observe motion. Now we're going to open this up with a couple new definitions. So first is a physical definition, in which we say that a reference frame is a collection of at least 3 non-collinear points in which the distances between the points do not change with time. And so what we're saying here in this physical definition is it's telling us that reference frames are attached to things. Okay? So if you think about something that has 3 non-collinear points in which the distance don't move, then that's essentially a rigid body. So we're sort of taking this idea of a reference frame and saying, imagine that it's attached to something. But it does beg the question, why do you need 3 non-collinear points? What's the purpose of that? So let's demonstrate that. Alright, let's draw 3 points. We'll just draw a point O. We'll draw a point P. And let's put another one up here at point Q. And these 3 points make a plane. So we've got the plane OPQ. Right? So if we have this plane, then the reason why we need 3 points is because we have a plane, and we can describe the orientation of any plane in 3 dimensions if we know a vector that's normal to that plane. So if we draw a vector on here that's normal to the plane, and I'll put it at point O, this can be our vector. We'll call it N to make it normal to the plane. And so that's normal to the plane. And we define this vector N by using the points that we have. And so to describe N, we can say that we've got a vector from O to P, which we know how to write that, which is R of P with respect to O. And we have the vector of O to Q, which is R of Q with respect to O. And so we can define the vector N as the cross product of R of P with respect to O crossed with R of Q with respect to O. So once we've got this vector N, that really gives us the tools that we need to describe the orientation of that plane in those 3 dimensions. Now, we want to make this a little bit more convenient for us, so let me make this a little bit bigger. And so, what I mean by convenient is that we have typically drawn our reference frames as 3 lines that are orthogonal to each other, right? So, let's draw those 3 lines. We've got a line. Let's define our first line as a reference frame, or as a line that's going from O to Q, or pass through Q. Let's define our second line for our reference frame as starting at the origin O and going up through that vector that's normal to the plane. And then our third line being a vector that's normal to the plane created by the line from O to Q and the line that's normal to the plane. And so there's our 3 lines that we've been drawing for our reference frames. We stick some arrows on those, and we'll call this reference frame I, which is telling us that this is an inertial reference frame. And we say that the reference frame I is going to be equal to a reference frame that has an origin O, and then remember, we said earlier that we define this with 3 vectors. So let's call these vectors E sub 1, E sub 2, and then E sub 3. So you'll see these E vectors as a pretty common notation that we use here. And remember, when we put a hat on top of a vector, that's telling us that it's a unit vector in the notation we use in this class. And so we've got our E vectors, we have an origin of O, So now we need to define where those vectors are. Let's make this such that we can use it. All right? So let's start out with that. We're going to define our first E vector, E1, and we'll just define it along this line that's going from O to Q. Now, E sub 1, we said, is a unit vector. And if it's a unit vector, it needs to have the magnitude 1, and so we define it this way. E sub 1 is equal to the position vector of R Q with respect to O divided by the magnitude of R Q with respect to O. Easy enough. So that's our unit vector pointing in this direction, E sub 1. Now we need to define an E sub 2. We can say that E sub 2 is going to point up. So by up, it's going to be this line along the vector n, or the line that's perpendicular to the plane. That's our qualitative definition. And to get E sub 2, right, we said this is our vector n divided by the magnitude of the vector n. That's the definition of our unit vector. And remember, we've already defined n as the position vector from O to P crossed with the position vector from O to Q. Looks like I forgot my underline. But we'll define this here. P with respect to O cross with R of Q with respect to O divided by the magnitude of P with respect to O cross with the position vector of Q with respect to O. And then that's giving us our unit vector E sub 2, which is along this vertical axis. So then draw the unit vector there, so we know where that is. And then we've got one more unit vector to get, and that's E sub 3. So the easiest way to define E sub 3 is to say that it is E sub 1 cross with the unit vector E sub 2. Let's draw that unit vector on there. And there's our E sub 3. So now we've got three orthogonal unit vectors that are defining our reference frame. This is a reference frame that has an origin at the point O. Point O is fixed within the reference frame. And then our unit vectors, E sub 1, defining this direction, an orthogonal vector to it, E sub 2, and then another orthogonal vector, E sub 3. So our definition of our reference frame has now expanded from just a physical definition, which said that we've got 3 points, point O, point P, point Q, that are non-collinear and have a fixed position between each other. Their positions don't change with respect to each other with time. And now we have an operational definition. And that's at the bottom of the page. It says that a reference frame is defined as 3 orthogonal unit vectors and a point fixed within the origin or within the reference frame. That point is the origin, it's fixed in the frame, and then these vectors, E sub 1, E sub 2, and E sub 3, all have a fixed orientation with respect to each other. And now that we have this operational definition with these unit vectors defining our 3 orthogonal axes or our 3 orthogonal bases, we can now define vectors. And so recall that we can define systems, we can define vectors in any frame of reference, but to use Newton's law, we have to define our acceleration in the inertial reference frame. And that's the key. Newton said it has to be fixed to the stars. We've now made that more modern by saying that we have an inertial reference frame, and there are rules for that. But essentially, that's saying that if we want to track point P and we want to apply laws of mechanics to it, then when we use acceleration, we have to write this as the acceleration vector, and that's P with respect to some point fixed in the reference frame, and that's within the inertial reference frame. And recall that we talked about the time derivative, so that means that the time derivative has to be taken within the inertial reference frame, and if we're calculating acceleration, it's the time derivative of the velocity of P with respect to O, and that's calculated in the inertial reference frame, and that's where the velocity in the inertial reference frame is the time derivative within the inertial reference frame of the position vector of P with respect to O. Okay. Now recall we don't need a reference frame notation on our position, because that doesn't matter. It doesn't matter where you observe position. It's always going to be the same. It only matters where you observe the time derivative of position, which is velocity, and the time derivative of velocity, which is acceleration. Now that we've got an operational definition of a reference frame, let's put it into practice. So here, let's make a vector. We've got a reference frame A. A is defined as this reference frame that has an origin of O, and then the three basis vectors A sub 1, A sub 2, and A sub 3. You can see these are always orthogonal. That's when we write these basis vectors, we're assuming that they're orthogonal with respect to each other. So if we define a point now, and our point is point P, then we have a position vector that goes from O to P, and that position vector is R of P with respect to O, and we can write that position vector now in terms of these basis vectors. So it's R of P with respect to O is equal to the scalar A1 in the A1 direction plus the scalar A2 in the A2 direction plus the scalar A3 in the A3 direction. So we have a set of three scalars that define the position of point P with respect to point O. And so now we've got a vector definition of that location of P. So you can see also that it's important here to notate or to use correct annotation of what's a scalar and what's a vector. So I've said before that whenever you make a vector, you're showing something as a vector, it needs to have a hat on it or an underline. And we've said that an underline is a vector, something that we're going to use, just a normal vector, and then a hat is going to be something that's a unit vector. So what we've done here is that we've got this position vector, and remember, a vector exists whether we like it or not, and it's up to us to define it. We've now defined this position vector, R of P with respect to O, in the A1, A2, and A3 basis. And that's within the reference frame A. So what we can do is we can describe this vector in the reference frame A. We can also describe this vector in a different reference frame. So let's draw a reference frame B. And so we'll keep the same origin, but we're going to define three new basis vectors, B1, B2, and then B3, and then show how that we can define that same vector in a different reference frame. And what we're going to do for B1, for our basis vectors, is we're going to define B3 as equivalent to A3. So what we're saying here is that for A3, that direction, we have a B3, which is in that very same direction. And then our two other basis vectors for our reference frame, B is going to be as if we rotated A1 and A2 within the plane made by A1 and A2. All right, so what this looks like is this. So there are lines that are defining the reference frame B, and then we have a vector A1 or B1, and then a vector B2 along these directions. And so we can even put, if we'd like to, what the angle is, so we can define this, what the angle is of our rotation between these reference frames. Now, using our new basis, which is B1, B2, and B3, we can define this same vector, R of P with respect to O, with a new set of scalars. B1 in the B1 direction plus B2 in the plus B2 in the B2 direction plus the scalar B3 in the B3 direction. And so we have this new set of scalars that are defining this same vector, right? So just to reiterate that, we've got a position vector, and that position vector can be described in any basis. It can be the A1, A2, A3 basis, or the B1, B2, B3 basis, as long as we have well-defined directions on those vectors. And so these set of scalar coordinates are a couple of coordinate systems. So what we say is R of P with respect to O. And if we take this vector and we describe it in the basis that's fixed within reference frame A, then our scalars are A1, A2, and A3. And we know that because we've already defined what the basis is, the directions, unit vectors A1 and A2 and A3. And so our scalars for our position vector within the reference frame B is equal to the scalars B1, B2, and B3. This is how we write that. Now these scalars, okay, and I hope this is clear, these scalars, A1 is not equal to A1 is not equal to B1, A2 is not equal to B2, and A3 is not necessarily equal to B3. Except in this situation, A3 is equal to B3, and the reason why is because our A3 and B3 basis vectors are pointed in the same direction. So with this in mind, I encourage you to look at examples 3.2 and 3.3 in the book, in which they work with these two different bases, two different reference frames and bases to track the motions of objects. All right, let's finish up looking at three commonly used coordinate systems that you'll see often in this class. The first is Cartesian coordinates, then we'll talk about polar coordinates, and then path coordinates. And so for Cartesian coordinates, this is really kind of old news. You've been using this for a long time. So let's first define our reference frame. It's always our first part. We're going to call this our inertial reference frame. We have an origin at point O, and our reference frame with the origin at point O, basis vectors of E sub 1, E sub 2, and E sub 3. And those vectors, we'll call this the E sub 1 direction, our E sub 2 pointing up, and then our E sub 3 is pointing directly out of the paper. Right. So now that we have our reference frame, we have this vector, and this vector goes from O to P. Okay, we're talking about position vectors, so it's R of P with respect to O. And then in this basis, R of P with respect to O is going to be a coordinate in the E1 direction plus a coordinate in the E2 direction. So for our Cartesian coordinates, we need to define our positions. So we have a coordinate in the x direction, and then we also have a coordinate in the y direction. It's going to define that position. So for Cartesian coordinates, it looks like this, where we have x in the E1 direction plus y in the E2 direction. And so the scalars for our Cartesian coordinate are P with respect to O, defined, this is in the inertial reference frame, is equal to x and y, and we'll put a subscript I, saying that these coordinates, these scalars, we're looking at this in the inertial reference frame. These are our Cartesian coordinates. Now let's define our polar coordinates. And for polar coordinates, we have a radius and an angle. And I think you've seen this before in physics. So we need to find an angle with respect to one of our lines in our reference frame. And so we'll define that angle as theta. And then we'll define the length of the vector, as we're tracking this point P, the length of the vector being r, the radius. And so r of P with respect to O is going to be the same because it's going to be the same magnitude of scalar multiplied times the basis vector. So our scalar in the E1 direction is going to be r cosine theta E1, and our scalar in the E2 direction, we're going to add r sine theta E2. And so here, this actually is the same because x is equal to r cosine theta, and y is equal to r sine theta. So here, converting between Cartesian coordinates and polar coordinates is actually pretty easy to do. We've got two Cartesian coordinates, an x and a y, and they're equal to the polar coordinates, r cosine theta and r sine theta. But the polar coordinates, there's an r coordinate and a theta coordinate, but they're combined to make the x and the y. And so to convert between these two coordinate systems is pretty easy. Here's our conversion. X is equal to r cosine theta, and y is equal to r sine theta. And so you can see how we can take these two coordinate systems and then we can track the particle as it's moving along this path. Now this brings us to our last coordinate system, which is a path coordinate. And so path coordinates behave very differently than Cartesian coordinates and polar coordinates. And the main difference is that in a Cartesian coordinate system or a polar coordinate system, we need two coordinates for each of those. Cartesian coordinates, we need an x and a y. For a polar coordinate system, we need an r and a theta to define the position of that particle at every time point. But for a path coordinate, it's defined as we only need a single scalar or a single coordinate to define that position. And so we draw that by saying we've got some starting point, and then we're going to trace the point P along the entire path, and so we only need the scalar of how far it's actually moved on that path to define that position. Now what that means is that if we're only going to use a single scalar, then we need to have a very well-defined mathematical description of what that curve or what that path looks like. Truth be told, we rarely have this. So path coordinates aren't terribly useful when looking at position, but path coordinates are very, very useful, and they come in handy when we're only concerned about the velocity and the acceleration of the particle. Alright, let's apply this to a simple pendulum. So this is going to be a non-inverted simple pendulum. In the last lesson, we had looked at an inverted simple pendulum, and also an earlier example in this lesson had that as well. So we want to express the motion of the pendulum in three coordinate systems: the Cartesian coordinate system, polar coordinate system, and path coordinate system, located in an inertial reference frame. So the very first thing we need to do is show that reference frame. So we'll draw our lines that define our reference frame, one to the right, one pointing down. I'm going to put the E2 basis to the right, the E1 basis vector pointing down, and so that still allows us to have E3 pointing directly out to us. So that's the inertial reference frame with an origin of O, E1, E2, E3. You need to write this for every problem that we do. And so after we've defined our reference frame, we've defined our basis vectors on our reference frame, we need to define gravity. Gravity is pointing down in this problem. And so now we start working through our coordinates. So first coordinate system that we're going to have, Cartesian coordinates. We are defining the position vector of r, p with respect to O. And to define that using Cartesian coordinates, we're going to have a scalar x, and then we're going to have a scalar y pointing down. And so the position of P with respect to O is going to be in the first basis, E1, that'll be y in the E1 direction, then plus x in the E2 direction. Okay, moving on to polar coordinates. We need two coordinates. We need an r and a theta. We'll define our coordinate r as being the distance from the origin, the scalar distance from the origin to the particle, and we'll define theta as being the angle of that position vector with respect to E1. And so in polar coordinates, r of p with respect to O is going to be r cosine theta, so r cosine theta in the E1 direction, plus r sine theta in the E2 direction. Oh, I should have mentioned earlier that we do have a constraint in our Cartesian coordinates, and so this is where x squared plus y squared is equal to L squared. And so we do have a constraint also in our polar coordinates, and that's where r is equal to L. And so that's how we've now recognized that this system has 1 degree of freedom. Even though we're using 2 coordinates, x and y, it still only has 1 degree of freedom because those coordinates are linked with each other through this constraint equation, x squared plus y squared is equal to L, and then in polar coordinates, it's this constraint equation, which is r is equal to L. So let's define the position of particle P in path coordinates. Now we just got finished saying that in order to define the position with path coordinates, we have to have a well-defined mathematical description of the curve or of the path in which it's on. And in this case where we have a simple pendulum, we do have a well-defined mathematical description, and that's that the particle P can only move in a circle around the origin O. And so our path coordinates is going to be S, because remember it's a single coordinate, and so we have S as a scalar, and that path is the arc length of that circle, the arc length being the radius L multiplied times the angle theta. So in this case we do have a well-defined version of this path, and it's L multiplied times theta. Alright, so each of these coordinate systems, it's important to note, are all in the same reference frame. Okay, we're only using a single reference frame. This is our inertial reference frame, and within this reference frame we've defined Cartesian coordinates, which are x, y, and z. Z is equal to 0 in this case. Polar coordinates, in which our 2 coordinates are r and theta, and then we also have z in polar coordinates, but once again we're in a plane, so z is equal to 0. And then path coordinates. The unique thing about a path coordinate is that it's a single scalar, it's a path coordinate, and in order to use it for position, recall that we have to have a well-defined mathematical description of the curve, and you'll see later when we get into path coordinates toward the end of the chapter that it is very, very useful for defining velocity and acceleration, which, remember, when we're applying laws of mechanics, we need acceleration. Alright, thanks. See you in class.